Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 2 of the course, and in this section we're going to continue with our preliminaries for group theory, and we're going to specifically discuss equivalence relations and functions and mappings, functions/mappings in this section. Okay, so let's go ahead and jump into it. And we'll call this section 1.2 of this course, and again, preliminaries, equivalence relations, and functions mapping. So let's start with equivalence relations. So we're going to begin with equivalence relations, and let's see here. Let me write this, equivalence relations. So things that are considered different in one context may be equivalent in another context. This is kind of the idea behind equivalence relations. This is part of the idea behind equivalence relations. So sometimes things look different, but given the context, they may be the same or equivalent. So simple example, 2 plus 1 is 3, and 4 plus 4 is 8. Right? In ordinary arithmetic, we would say that 3 and 8 are different. Right? In ordinary arithmetic, these are different. Right? Nothing too novel there. But what about in modular arithmetic? In modular arithmetic, right, the rules change. What we consider the same in modular arithmetic changes. So in particular, 3 mod 5 is 3, and 8 mod 5 is 3 as well, right? So in modular arithmetic, mod 5 in particular, right, in that case, 3 and 8 are equivalent. We say that 3 and 8 are congruent to one another, actually. Okay. All right, so this is just an example. So sometimes things appear different depending on what the context is, right? And this is a clear example of that. You've got two digits, 3 and 8, which are totally different, seemingly in terms of ordinary arithmetic, but are equivalent to one another in modular arithmetic, mod 5 in particular. Okay. And so the idea for an equivalence relation kind of comes out of this notion, right? So what I'm going to lay out here in terms of this definition of an equivalence relation, you can kind of think of it as a formal sort of mechanism for specifying whether or not two quantities are the same, equivalent, given a particular setting. Okay, so it's a mechanism for determining whether or not two quantities are equivalent given a particular setting. So the setting matters. Okay, so here's the definition. An equivalence relation on a set S is a set R of ordered pairs of elements of S such that what? Well, so an equivalence relation on a set S, we're going to think of it as a set of ordered pairs, and the ordered pairs, the name of the set we're going to call R. Okay, R for relation, right? So an equivalence relation on a set S it's a set of ordered pairs. Now the ordered pairs have to have certain qualities, though, right? And so what are those qualities? Well, first of all, A comma A must be in the relation, right? So that's for all A and S. Right? So basically what we're saying here is that A is equivalent to itself, right? This is the reflexive property. Okay. Right. The second thing that we require is that if A and B are in the relation, then B and A must be in the relation as well, and that's going to be for all A, B, and S. All right, now what is this called? Well, this is symmetric, or symmetry, right? So the relationship has to be symmetric. If A is equivalent to B, then given that it's an equivalence relation, we require B be equivalent to A. So there's a symmetric ness to the relation. All right, and the third item is that if A and B are in the relation, and if B and C are in the relation, then that's going to imply that A and C be in the relation as well, right? And you'll recognize this as transitivity. Right? If A is related to B and B is related to C, then A must be related to C as well. Okay. And so this is, like, loosely speaking, precisely speaking, this is the definition of an equivalence relation. All right. And just a word on notation. Let me flip the page here. A word on notation, because the notation here can get a little loose at times. So I just kind of want to say up front what we'll use. So we will frequently use the notation A related to B instead of A comma B in R. Right? It means the same thing though. A related to B is the same thing as saying A and B are in the relation. Okay, and so the other thing is that we will also frequently use notation like this. So like something like this, or like that, or even something like this in place of the typical equality, right? And equivalence and equality, they don't mean the same things exactly, right? So they sort of rhyme in places, but they're, when we say two things are equivalent, we don't necessarily mean they're equal, right? It doesn't necessarily rise to the same meaning. So and so this is specifically to separate it from the idea of equality. So to separate equivalence from the idea of equality. Okay, so just something to note. Right, so we'll frequently see things like this, right? Or A equivalent to B implies B equivalent to A, okay, etc. That kind of stuff. Okay. All right. Okay, so that's kind of the rough idea of what we mean by an equivalence relation. Let's see some examples. Well, let's start with a definition of a very closely related idea, and then we'll jump into some examples, lots of examples. So if tilde squiggle is an equivalence relation, so if we have an equivalence relation on a set S, and A is in S, then the set, and it's denoted like this, A in kind of brackets like this. This is the set where this is the set of all X in S such that X is equivalent to A. So all of the things from S that are equivalent to A, that's what this set is called. Well, that's what this set is, and the set is called the equivalence class. Okay, so if tilde is an equivalence relation on a set S and A is a member of S, then the set of all things that are equivalent to A is called the equivalence class of S containing A. Okay. All right, so this is the idea of an equivalence class. Okay, let's see some examples. This might be getting a little, this could be getting a little abstract here for us. So let's take a look at some examples, some concrete examples, if possible. Okay, here's a good one. Let's let S be the set of all triangles in the plane. All triangles in the plane. Okay. Okay, and so we've got a big set, right? Infinite set here. Set of all possible triangles. So you've got right triangles, acute triangles, obtuse triangles, this kind of triangle, that kind of triangle, all the kinds of triangles you can imagine. Okay, so if A and B are triangles in S, right? So S is the set of all such triangles. If A and B are particular triangles in S, we're going to define A equivalent to B if A and B are similar triangles. Okay. Now, hopefully we remember what similar triangles are, right? Triangles are similar if they have the same angles. If A and B are similar if they have corresponding angles that are the same, right? So let's say I have, this is my set S, all possible triangles. So one such equivalence class would be the 60, 60, 60 triangles, which kind of look like this. And so I've got a 60, 60, 60 triangle with a certain length, and then I've got some that are smaller, some that are larger, some that are really small, but they all have the same shape, don't they? Meaning they're all 60, 60, 60 triangles. So that's an equivalence class. Everything in this set is equivalent since they're similar. Right, another sort of triangle would be like a kind of a right triangle, maybe a 30, 60, 90 triangle. Right, and there's a whole bunch of different ones, infinitely many different triangles that are 30, 60, 90 triangles. Right, these are all right triangles, 30, 60, 90, etc. Infinite set, infinitely many variations of similar types of triangles. Right, but you can see how this is an equivalence, how this equivalence relation would work. Okay, that's a good one. I like that one because it's very concrete. You can picture it. Okay. How about this example next? So let's let S be the set of all polynomials with real coefficients. So S is the set of all polynomials with real coefficients. Okay, real valued polynomials. All right. So if F and G are polynomials in S, we're going to say, let's define F is equivalent to G if F prime, the derivative of F, equals G prime. Well, here we're talking about the derivative, right? Where F prime is the derivative of F. Okay. Right. So we've got all possible polynomials with real coefficients. We say two polynomials are equivalent if their derivatives are equal. Okay. So because two functions, two polynomials with equal derivatives, they're going to basically differ by a constant, aren't they? So because two polynomials with equal derivatives differ by a constant only, right? We can say that the equivalence class given a particular F is just going to be basically equal to the set of all F plus C, right? Where C is some real number, basically. Right, so an example would be like all of the polynomials where the derivative is 1. Let's say f prime of x equals 1. Right, and so that would be like things like f1 of x equals x, f2 of x equals x plus 1, f3 of x equals x plus 1.5, etc. Right, and so all of those polynomials are going to be in the same equivalence class. Right, they're just basically whatever the base polynomial is plus or minus a constant, plus a constant, right? Right, and so this is an equivalence relation on S. Right, so we could say that this is an equivalence relation on S. Okay. Another good example, kind of, one you can picture, right? If you remember your calculus, you can remember what happens with derivatives of polynomials, right? And how there are infinitely many polynomials whose derivative is 1. Infinitely many polynomials whose derivative is x plus 2, for example, would be another one. That'd be another equivalence class. Okay. Very good. Let's see, what else could we... Let's do another example here. Examples are key in abstract algebra. You'll see I'm not only in the preliminaries, but also when we get into the groups, we'll talk about many, many examples. So for the next example, let's let S be the set of integers. Okay, so let S equal the set of integers, and let's let n be a positive integer. Okay, so a natural number. If a and b are in S, right, i.e. they're integers, let's define a is equivalent to b if a mod n equals b mod n. Okay. Right. And so we saw previously another way to characterize this is i.e. if n divides a minus b. Right, we saw that previously. Right? Then, we could say that this is an equivalence relation on S. Right? It's an equivalence relation on S, and we could actually write out the equivalence classes, right? So the equivalence class for A would be equal to the set of all A plus k times n, where k is any element in S. Okay, that would be an equivalence class. Now for this one, because this is something we've talked a little bit about the modular arithmetic in the previous section, let's actually go through and verify that this is an equivalence relation. Let's verify that this is an equivalence relation. And to do that, what do we have to do? Well, we have to verify that this relation is symmetric, reflexive, and transitive. All right, so let's start with reflexive. That's the easiest one usually. Right, and so we need to show that A is equivalent to A. Well, A is equivalent to A, yes. Why is that? Well, because n, whatever it happens to be, is always going to divide A minus A. Right, remember it's important here, and I didn't emphasize it above, I stated it, but it's important to remember that A mod n is equal to B mod n when that's an if and only if n divides A minus B. And you would probably recall from the first lecture that we proved that. We wrote a proof of that theorem, And so make sure make sure you understand that. Make sure you recall that theorem and we're able to walk through that proof, because we're going to take it for granted going forward. Right? And so this is an obvious case where if A is in an equivalency class, then it's equivalent to itself. And the reason is because n is going to definitely divide the difference between a minus a. Any number divides 0, right? Right. It's another way to say it. Well, because n divides 0, right? So it's reflexive. A is always equivalent to itself. What about symmetric? Well, let's assume that A is equivalent to B. Okay, so let's assume that. Then A minus B is equal to some Rn, right? Right, because A being equivalent to B means that n divides A minus B, so just using the division algorithm, there exists some integer r such that A minus B is equal to r times n. Okay. Right, and so we're going to do some algebra on this. Let me bring it down here. Okay, so we're just going to do some algebra. We're going to multiply by -1 on both sides, like so. And that means B minus A equals -r times n, right? Which means what? Well, this implies that n divides B minus A, right? It doesn't matter the integer. If r is an integer, then -r is an integer also. Okay, so if n divides A minus B, then n also divides B minus A. That may not be something you're aware of, but that is a fact. And so B is congruent to A. B is equivalent to A, we'll say. We're not really using the congruence language here, but B, if A is equivalent to B in this setup in terms of modular arithmetic, then B is equivalent to A. All right. And then the final property is that we need to prove that the equivalence is transitive. Well, we need to prove that the relation is transitive in order to show that it's an equivalence relation. Okay, so transitivity. So we're going to need to assume that A is equivalent to B and B is equivalent to C. So assume A is equivalent to B and B is equivalent to C. Then, right, A equivalent to B implies what? It implies that A minus B equals Rn. And do the same thing for B and C. B equivalent to C implies that B minus C equals Sn. Okay. Then what about A minus C? Well, A minus C, we'll see, is equal to A minus B plus B minus C. That's just algebra. And A minus B we know is equal to Rn. And B minus C is equal to Sn. Oops. Okay, and so that's equal to R plus S times N. Right? And so this fact here, so A minus C, so I'll just write it again, A minus C equals R plus S times N. That implies specifically that N divides A minus C. Okay, and so that means A is equivalent to C. Okay, and so these three properties, when these three properties hold on a relation like this, that means it's an equivalence relation. And that's exactly what we were after. That's exactly what we were after. Let's do an example with this relation. So let's let this equivalence be as in the previous example. So this is just like the previous example, and let's let n equal 7. Okay. then we can say a few things, right? We can say lots of things, actually. But what we can say for sure here is that 16 is equivalent to 2. Right? And why is that? Well, because 16 is equal to 2 times 7, 7 being the modulus here, plus 2. Right? So the remainder is 2 there. We can say that 9 is equivalent to 5, right? Because 9 equals 1 times the modulus 7 plus 5, right? The remainder of 5. Okay. Etc. Right? We can go on. So 24 is equivalent to 3. Right? And that's because 24 equals 3 times the modulus 7 plus 3. So 3 times 7 is 21, plus 3 is 24. So 24 and 3 are equivalent. Okay. All right. Okay, let's list some of the equivalence classes here. Right, and so we've used this visual. I think we used this in the last lecture. But if I have modulus 7 here, and I start to kind of mark off from 0, just kind of count up, and where does everything fall? So 0, 1, 2, 3, 4, 5, 6, 7. We start to wrap around here. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and so on. I could keep going, right? Then what are the equivalence classes? So let's think about 1. What's the equivalence class for 1? Well, it's all of the things that are equivalent to 1 modulo 7. Right, that are all of the integers that are congruent to 1 modulo 7. So let's just think about the positive side. So it's 1, 8, 15, 22, and so on, right? Now the negative numbers would be there as well. They're not in my picture, but you can imagine if there was some way to kind of wind this the other direction into the 7, you would have them, right? And so on, right? What about like the equivalence class for the number 4? Well, you would look here, 4, 11, 18, 25. Those are the positive values. 4, 11, 18, 25, and so on. And then the negative values would be there as well, so like -3, -10, etc. Right? And so these are the equivalence classes. In this case, you can kind of picture at least the positive side of the equivalence classes as kind of the branches on this spiraling, this way of laying out the positive integers in this kind of spiraling. It kind of spirals out like that. So those are the equivalence classes for this modulo 7 relation. Okay. Let's take another example. Let's look at another example. This time, let's let S equal the set of all A and B such that A and B are integers, with B not equal to 0. Okay, so that's our set. So basically all ordered pairs of integers where B is non-zero. Okay. Then, if AB and CD, 2 ordered pairs, are in S, we're going to define AB is congruent or equivalent to CD if, this is kind of a weird one, A times D equals B times C. Okay. All right, so this is kind of a weird one, right? So we've got a set S of all ordered pairs of integers, right, with the second term non-zero, right? So if I have two sets of ordered pairs in S, then they're equivalent to one another if A times D equals B times C. So if the two outer components multiplied together equal the two inner components multiplied together. Okay. And so this is an equivalence relation. On the set S. Okay. So let's test that. Let's test that this forms an equivalence relation. So we got to test reflexivity, symmetric, and we got to see that the relation is reflexive, symmetric, and transitive. So let's look at reflexive first. Okay, so A comma B is symmetric to A comma B. Obviously, it's related to A comma B because A times B, the two outer ones, A times B, is obviously equal to B times A. Okay, that one's straightforward. Okay, so A times B equals B times A, so AB is equivalent to AB. Okay, not a problem. What about the symmetric property? Do we have that? Let's see. So A comma B, C comma D. Right. So here's what we need to show. Okay. So A comma B equivalent. So AB equivalent to CD implies what? Implies that AD equals BC. Now, I can flip the order here, right? Let's see here. So let's see what I'm going to do. So instead of AD, I'm going to write DA. And instead of BC, I'm going to write CB. Okay, not a problem. Now, that's just because these are integers, right? And they commute, right? The multiplication is, I can commute the multiplication, no problem. The other thing that is obvious that I can do is instead of writing DA equals CB, I can write CB equals DA, right? That's just, hey, they're equal, right? So it doesn't matter if I say, you know, such and such is equal to A is equal to B. I can just as easily say B is equal to A. I can flip the order, not a problem. Well, this right here is just exactly what we want. So this is C comma D equivalent to A comma B, right? The two outer, C times B equals the two inners, D times A, D times A. Right, so AB equivalent to CD implies that CD is equivalent to AB. Very simple to get to that one. All right, and then the last one that we need to show is the transitive. We need to show that the relation is transitive. Okay, so we'll assume that AB is equivalent to CD and CD is equivalent to EF. Okay. Right, so AB equivalent to CD, let's just write all this out, implies that AD equals BC. And I'm going to call that 1. We're going to have to label these things to come back to them. Okay, and then secondary, so that's this one. What about this one? So CD equivalent to EF implies that C times F equals D times E, and we're going to call that 2. Okay, now what we're going to do is we're just going to show that this is going to imply that AB equals EF, or is equivalent to EF. We're going to show that AB is equivalent to EF through this operation, through this transitive, and hence the relation is transitive. Okay, so from 1, here's how we'll do it. It's pretty straightforward, but I guess you have to kind of think a little outside the box at first. So AD equals BC, and I can simply multiply both sides by F. And so AD, I'll put that in parentheses, equals BC times F, right? So just multiplying both sides by F. Okay, and I'm going to drop the parentheses on this side and say ADF is equal, and I'm going to change the order over here. I can do this as just multiplication of integers, right? So instead of BCF, I'm going to write B times CF, like so. Okay, and so now I've got ADF is equal to, now instead of CF, right, I'm going to put in DE, right, CF, DE. So instead of CF, I know CF is equal to DE, so I'm going to put B times DE, like so. Okay, and so now what do I have? I have ADF equals BDE. I kind of drop the parentheses. And I'm going to just rearrange this a little bit and write AFD, just change the order, put the D on the one side, just make it clear what I'm doing, and then BE times D. And I can cancel off the D's, and I have AF equals BE. And that basically means that AB is equivalent to EF, which is what we're trying to show. Right, so AB equivalent to CD. AB equivalent to CD and CD equivalent to EF implies that AB is equivalent to EF. Okay, and so that's the sort of the verification of that example of an equivalence relation. Kind of a different one, right? So like a weird. These can be as weird as you like. I mean, as long as they meet the threshold definition of an equivalence relation, then you're good. This is one that is kind of unintuitive, though, but works out. Okay. Next up, we want to talk a little bit about partitions. Okay, so I want to define a partition. Maybe people have seen a partition, the idea of a partition, but let's define it. We'll use it a lot. A partition of a set S is a collection of non-empty disjoint subsets. So non-empty disjoint subsets of S whose union is S. Okay. So a partition, if I have a set S and I want to partition it, what I'm basically doing is breaking it up into a collection of non-empty subsets that are all disjoint, meaning they have an empty intersection, and whose union equals S. Right, so like the classic picture would be to just draw a set S like this, and then to break it up into different pieces. So here's a subset over here, here's another subset over here, here's a subset here, and there's a subset over there. All right, so here S is partitioned into 4 subsets. Right, and then the understanding is that the boundaries of these sets do not overlap. Right, there is no intersection. Okay, let's see some example. Let's see an example here really quick. So that's kind of the classic sort of drawing of a partition. A basic example would be like, we can partition the integers into, well, the set containing 0 and the set of positive integers and the set of negative integers. Right? Obviously, the union of these 3 sets equals the integers, and clearly they have an empty intersection, right? One's positive, one's negative, and one is just a singleton 0. All right, so that's what we mean by a partition. And what we want to do is we want to tie this idea of a partition into the concept of equivalency classes. So the next theorem shows us how these two concepts are related. Okay, so the next theorem shows us how partitions are related to equivalence classes. So let's get to that theorem. This is a nice theorem. Okay, so the theorem says that the equivalence classes of an equivalence relation on a set S, of course, constitute a partition of S. Okay, so given a set S, the equivalence classes, right? Remember those sets that we defined earlier, where, you know, we'll bring them up again if you can't remember, but look back a couple pages. You notice the equivalence classes of an equivalence relation on some set S, they're going to end up actually partitioning S. Everything in S is going to be in some equivalence class, and none of the equivalence classes will overlap with each other. There'll be no intersection. So that's the first part of the theorem. That's the first part of the theorem, which is awesome, amazing, right? Or common sense, sort of depends on how you're thinking about it. Okay, it's at first you might say, "Whoa, that's not obvious," but it is slightly obvious when you think about it a little deeper. But it is a big idea, I think. Right. So the equivalence classes of some equivalence relation, they're going to partition the set on which the equivalence relation is defined. Okay, so that's one part of the theorem. Then conversely, for any partition, and we'll denote it P of S, the set S, there is an equivalence relation on S whose equivalence classes are the elements of P. Okay, so that one is also interesting, right? So given a set S and any partition you can think of, right? Any partition you can think of, for that partition, there is an equivalence relation whose equivalence classes are the elements of your partition, your chosen partition, as arbitrary as you like. Okay, so that is the theorem here that kind of relates partitions to equivalence classes. Now we're going to prove this theorem because it's a big theorem and it's an interesting theorem. Oops, 1 second. Drop my paper. Okay, so let's write a proof for this guy. Let's see if we can get this one understood. Okay, so let's prove it. We'll start with the first statement. The first statement, remember, was that the equivalence classes of an equivalence relation on a set S constitute a partition of S. Okay, so we're gonna let tilde here be an equivalence relation on a set S. Right, so we've got an equivalence relation on our set S. Now, for any A in S, by reflexivity, right? It's an equivalence relation after all. By reflexivity, we have A. So we need to first show that we've got a non-empty subsets here. So for any A in S, by reflexivity, A is going to be in the equivalence class of A, right? And so that means the equivalence classes cannot be empty, right? However they're defined, they can't be empty. Okay, hopefully that's clear. Okay, this being the case, the union of all of these equivalence classes must be S. Right, so this being true, the union of all, right, because again it said for any A and S, this is true. Any A and S, is going to belong to its own equivalency class, right? And so that being the case, the union of all such equivalence classes must equal must be equal to S. So that being true, the union of all equivalence classes must be S, right? So that one's kind of straightforward. Okay, so we know that. So remember, the definition of the partition was what? It's a collection of non-empty disjoint subsets whose union is S. So we've shown that the subsets are non-empty. These equivalence relations are non-empty, and that the union of all of these equivalence relations is S. Now what we need to show is the disjoint piece. That's the part we haven't shown. So we know what? Let's write it down here. We know we've got the non-empty thing. We've got the union. We need the disjoint property. Still need that part, okay? So non-empty and union, you kind of get those together. Now we got to prove the disjoint. So to kind of put that plainly, let's suppose that you got the equivalence class of A and the equivalence class of B are, and we'll say A and B are disjoint, or sorry, not disjoint, that's what we need to prove, distinct equivalence classes. Okay, so what we must show is that they're disjoint. And by disjoint, what do we mean? We just mean their intersection is the empty set. Okay, that's what we need to show. All right, so the way we're going to do this, we're going to do it kind of by contradiction, right? We're going to derive a contradiction, right? So we're going to assume that C is an element in the intersection of A and B. Okay. Okay. So we're going to assume that C is in the intersection of A and B. And by that, we're going to end up showing that A is a subset of B. So let's let X be in A. So X is some member in A. Then we have what? C is equivalent to A, right? By C is in A and B. C is also equivalent to B, right? C is in A and B. And we know that X is equivalent to A, right? That's the thing we just said. Let X be in A. Okay. By the symmetry property, we also know that A is in C and B is in C and A is in X, right? So that's also, or sorry, A is equivalent to C. So by symmetry, A is equivalent to C, B is equivalent to C, A is equivalent to X. Okay. Okay. Then by transitivity, it follows that X is equivalent to C, right? X is equivalent to A is equivalent to C, so X is equivalent to C. So let's see, so we'll just say X is equivalent to A. We'll recap all of this in a second. Oh, sorry, X is equivalent to C. And also X is equivalent to B. Okay. Okay, let's recap. I think we went afar here, or we didn't go astray. I may have done a bad job itemizing these things. Let's itemize this a little better. So C is assumed to be a member of A intersect B. What does that mean? Well, it means C is equivalent to A and C is equivalent to B. Okay, secondarily, X is assumed to be a member of A. X is somebody in the equivalence class of A. And that means what? Well, with that we get that X is equivalent to A, obviously, if it's in the equivalence class of A, but then also A is equivalent to X. Okay. And so if we combine 1 and 2, X is equivalent to A, and A is equivalent to C. Well, right here, right? C is equivalent to A, is equivalent to C. Those two together imply that X is equivalent to B, or C, sorry. Man. Okay, and we could do something similar here. We could also say X is equivalent to C, and C is equivalent to B, implies that X is equivalent to B. Okay. Right, so if X is in A, and something in A is equivalent to something in B, it must be true that everything in A is equivalent to everything in B. Right? That's kind of the clincher, right? Right? So if X is in A, right, and something in A, let's just write this out, something in A is equivalent to something in B, right, then it must be true that everything in A is equivalent to B, everything in B. And another way to say that is to say that A is a subset of B. Now we could do the exact same exercise, but going the other direction, right? So the same exercise could be done to show that B is a subset of A, right? You could literally do the same thing. Instead of up here where I say X is in A, say X is in B. And you get the same thing. You get to the same result. You'd show that by assuming there's an element in the intersection and assuming something is in B, then that B is automatically equivalent to something in A, and hence everything is, right? And so if if the equivalence class of A is a subset of the equivalence class of B, and the equivalence class of B is a subset of the equivalence class of A, then this implies what? They're equal. Right? That's the implication, is that the equivalence classes are equal. And so obviously that's a problem, right? Because our assumption at the onset was that these were distinct equivalence classes. That implies a contradiction because we assumed A and B were distinct, meaning they were different. They weren't identical, right? And so the problem obviously came into play as soon as we had something in the intersection. Okay, and so this implies, the contradiction. To resolve the contradiction, we have to go back and change our assumption about the intersection, and namely, we have to understand that the intersection is empty. If the intersection isn't empty, we can derive a contradiction. Okay, and so that's the proof one way. Okay. Now the other side of the proof, remember the converse statement. Conversely, we were told that any partition P of some set S, for any partition P of a set S, there is some equivalence relation on S whose classes are the elements of the partition. So to prove the contrary, what can we do? Well, let's do that one. Now, so this is not an if and only if statement. It's kind of a two-parter, so let's talk about part two. Right? To prove this other one, we're going to let P be a collection of non-empty disjoint subsets of our set S whose union is S itself, right? Okay, so all we've said here is we got a partition, and it's a collection of non-empty disjoint subsets of S, right? Whose union is S. Namely, it's a partition, right? Now we're going to define. Here's where the magic comes in, right? So what the theorem says is that there's some equivalence relation such that the equivalence classes of this such that the equivalence classes are, make up the structure of the partition. Okay, and so the magic is all in how do you define the equivalence relation so that the equivalence classes are any arbitrary partition you can dream of. Right? And so it's a little tricky, but here's what we do. So we simply define A is equivalent to B if A and B belong to the same subset. In the collection. Okay. All right. So that's kind of tricky, right? So I know when I first heard this theorem, I thought to myself, geez, how are we going to what kind of an equivalence relation could there possibly be such that such that any arbitrary partition I can think of, the equivalence classes make up the partition. But the trick here is just to define the equivalence relation as A and B being equivalent if they belong to the same subset. That's it. It's very simple, actually, right? So you've always got this. But the question is, does this definition of an equivalence of a relation rise to the level of an equivalence relation? So we need to show that this relation is indeed an equivalence relation, right? Because that doesn't, just set membership is an equivalence relation. Okay, let's see. So we have to show that. So we have to show that it's reflexive first. Okay, so we're gonna let A be in S. Well, we'll let A be in some subset. We'll call it S1. Okay, so S1 is some subset of S, part of the partition. It's one of the sets in the partition. So we'll let A be in this subset. Then A is equivalent to A because, and this is almost abusive notation, because A is in S1 and meaning this one, and A is in S1. It's not abusive notation. It's just too obvious. It's hard to write it. It's so obvious. So obviously, the relation is A is related to A because they're both in the set, right? So obviously it's the same element. Symmetric. Do we have symmetry here? So let's let A and B be two elements of a subset 1. We'll say S1. Well, A equivalent to B and B is equivalent to A, well, because they're both in the same set. A is equivalent to B because A is in B's subset. B is equivalent to A because B is in A's subset. So that's fine. Right, and transitivity follows just as easily. So let A be equivalent to B and B be equivalent to C. Well, so A is equivalent to B means that A is in B's subset. B is equivalent to C means that B is in C's subset. So if A is in B's subset and B is in C's subset, then A is automatically in C's subset as well. Right? A equivalent to B means that A and B are in S1. B equivalent to C implies that B and C are in S1. B and so here I've got C in S1, here I've got A in S1. That implies that A is equivalent to C, right? So we've got the transitivity. So it's you know, in some ways, set membership is the most basic form of an equivalence relation. Okay, you just don't think of it when you first hear of the idea of an equivalence relation. You don't think, oh, set membership. But it's in some ways the most obvious form of an equivalence relation. Okay, so that gets us what we need for equivalence relations. Again, kind of an introduction, some of the bigger theorems, just kind of looking at them, refreshing our memory on what partitions are, etc. Now, the second half of the section of the lecture is on functions. I'm going to pause the video and have a part B for that section, just to kind of keep the videos of reasonable length. So we'll be right back with part B of this section of this lecture, where we talk through functions and mappings. So we'll see you then.